From this lecture onwards, let's take one embedded C program, that is a program which we have written for a microcontroller, and let's analyze that. So we are going to understand anatomy of the microcontroller. So identifying code and data parts of the program. So we'll understand the code memory and data memory of the microcontroller. And also we are going to explore the disassembly of the final executable using disassembly feature of the IDE. And also we are going to analyze the executable which is in the format .elf using GNU tools like object dump and size. Let's start. Alright, now first let's understand what is microcontroller. So a microcontroller, which is also abbreviated as MCU, which stands for microcontroller unit, is a small computer system on a single chip. But its resources and capabilities such as memory, speed, external interfaces are very much limited than of a desktop computer because MCU targets embedded applications. A typical microcontroller includes a processor, volatile and non-volatile memories, input-output interfaces, peripherals, clock unit, bus interfaces, everything on a single chip. So that's why a microcontroller is also called as a system on chip. So all the required units such as a processor unit, which is also called as CPU, peripherals such as analog peripherals such as ADC, DAC, timing related peripherals such as timers, connectivity peripherals such as UART, USB, and different types of memory such as volatile memory such as SRAM, non-volatile memories such as flash, ROM, EEPROM, clock unit, bus interface. So everything is implemented or fabricated on a single chip, and that's what we call as a microcontroller. All right, now let's understand anatomy of a typical small microcontroller. So now let's see what exactly is inside a microcontroller. This is one of the simplest diagram. The real picture may be complicated if you take a look into a modern microcontroller. So usually a microcontroller has a CPU inside. So that's what we call as a processor or a central processing unit. Now the central processing unit executes instructions, your program instructions. And those instructions are actually stored in a program memory. So usually program memory is a non-volatile memory. So that means once you store your program into the program memory, that is permanent. I mean, you can erase it, you can write different programs, but even if you take out the power from microcontroller, the program memory will not be corrupted. So your instructions will be there permanently unless you change it. So once you give power to the microcontroller, CPU actually reads instructions from the program memory and it executes. So that means before that, CPU should communicate with the program memory, right? So CPU is a different entity and program memory is a different entity, right? CPU communicates with the program memory using bus interfaces. So there is a bus called address bus because before reading an instruction, a CPU must produce the location or the address of that instruction, right? Which is there in the program memory. So CPU first produces the address on the address bus, and after that the instruction will then come into instruction bus, or you can also call it as data bus, and from that instruction will reach to the CPU, and CPU has something called instruction decoder. So CPU decodes the instruction and according to that action will be taken. So how fast CPU executes instructions depend upon the clock supply to the CPU. So all these things we'll see as we make a progress by taking industry standard microcontrollers such as STM32. So this is the simplest diagram which I'm showing to you. So there will be one clocking unit which will supply clock to the CPU. Depending upon the speed of the clock, the speed of code execution will be controlled. So apart from non-volatile memory, there is also something called volatile memory, which is called as data memory. So basically a program operates on data, right? So the data part or data of the program is actually stored in the data memory. So you can also use data memory as a scratch pad. That means if you want to store some data temporarily, then you can use data memory. So basically the data memory is consumed during runtime of the program because there are various occasions when a program needs to store and delete data temporarily. So in that cases, program can use data memory. So that's why it makes sense to use volatile memory as a data memory, right? As a scratch pad. So because we don't want that data to be stored permanently, right? That's why data memory is actually a volatile memory. So when the power is taken off from the microcontroller, the contents of the data memory will be lost. And apart from that, a microcontroller program also should communicate with the external world, right? Let's say you are sending some command from your mobile phone to the microcontroller over Bluetooth. So a microcontroller should communicate with a Bluetooth module, right? And that can be enabled by using the I/O interfaces. So there is something called serial I/O, parallel I/O. For example, if you want to connect a Bluetooth receiver to this microcontroller, then you would be connecting that Bluetooth module through serial I/O. So that's why I/O interfaces are very much important, and almost all microcontrollers support this feature. And let's see how a modern microcontroller looks like. Let's take an example of one of the most famous microcontroller, which is produced by ST Microelectronics, STM32 series of microcontrollers. This is a picture which is given by the ST documents, and here you can see that it actually shows all the internal parts of the STM32 microcontroller. Alright, so if you just take a look into this image, you can identify various parts of this microcontroller. The heart of this microcontroller is a processor, which is sitting inside the microcontroller. And in this microcontroller, that is STM32F407 microcontroller. So then what you see here is an ARM Cortex M4 based central processing unit. So that's a processor. So this processor is actually developed by ARM. So this is not actually developed by ST. So ARM develops processors and then it licenses to other microcontroller manufacturers. In this case, it is ST Microelectronics, and they actually take the software implementation of the processor unit and they customize according to their need. And after that, they implement it on the chip. So in this case, the ARM processor has the capacity to run at maximum of 180 megahertz. So that's pretty fast, right, for the embedded application. Apart from that, all these things what we are seeing here, it is implementation of ST. So they have implemented different peripherals around the processor. And all these are actually implementation of ARM. So if you just look at the peripheral set, so they have different peripherals to serve different purpose. For example, so these are connectivity related peripherals. So if a microcontroller wants to communicate with the external world, then connectivity related peripherals will be used, such as SPI, that is serial peripheral interface, camera interface, CAN, I2C, USB, so on. And for the analog work, you have digital to analog converters, ADCs, and temperature sensor, and various other things. And so these are control related peripherals. They actually don't communicate with the external world, but those are actually will help you to do control related activities like PWM, wave generation, timers, and various other things. And these are system related peripherals such as RTC, which takes care of real-time clocking. So it has PLL engine, so which is used to boost the clock. And the microcontroller has inbuilt oscillators. They are called as internal RC oscillators. So even if you don't connect any clock or any crystal to this microcontroller can run by using its default oscillators, which are right there inside the microcontroller. So you need not to connect any external crystal oscillators to this microcontroller. So it has the capacity to make use of internal RC oscillators. So those oscillators actually produce clock to the central processing unit and for various bus interfaces and to the peripherals. And it also has low power control circuitry. It also has internal power regulator, so which is used to produce regulated power supply to the microcontroller. And also it has watchdog timers. And let's take a look into the embedded memory. So these are the embedded memories which are there inside the microcontroller. So it actually uses a flash for the code memory. So flash is used for the code memory, and SRAM is used for data memory. So SRAM is actually volatile memory, and a flash memory is actually non-volatile memory. So inside the flash memory, you are going to store your instructions. And apart from that, it has external memory interfaces if you want to connect more external memories such as flash memory or SDRAM memory. And also it has OTP memory, that is one-time programmable memory, and all these are actually internal memories. And this is how a modern microcontroller looks like for the embedded applications. Let's take an example of PIC microcontroller. PIC stands for Peripheral Interface Controller, which is a quite famous microcontroller in the 8-bit application domain. And this microcontroller is manufactured from the company called Microchip. And if you take a look into its internal parts, it is almost similar to the previous one. But here also there is a central processing unit, but this is not an ARM processor, remember. So this is actually a proprietary processor design from the microchip itself. It's their own CPU architecture. You can call it as PIC architecture. It's their own CPU. So that's why it has its own instruction set. So that's why the code what you have wrote for STM will not run on microchip until you cross compile it again using the compiler which is produced by Microchip. So apart from that, you can see that it also has internal oscillators, right? So in order to produce clock, a default clock to the CPU and for the peripherals. And it has various peripherals similar to previous one, and timers. It also has a program memory, data memory, and it also has on-chip WFROM and the I/O ports to communicate with the external world. So the analog peripherals, timers, PWM. So it's quite similar, right? Let's take a look into another embedded board here. So this is a TIVA development board, which is produced by Texas Instruments, and it carries a TIVA series of microcontroller. So this is a microcontroller, and this microcontroller is also based on ARM Cortex M4 processor. So in this case, the maximum achievable speed is 80 megahertz. And this microcontroller also has various embedded memories. So you can see here, it also has 2 kilobytes of WFROM. These are all the analog peripherals. It also has various connectivity related peripherals. And these are some of the other peripherals. So the peripherals to include and peripherals to exclude. So all these are actually driven from the marketing end, and it depends on the application area which the microcontroller targets. So at the end of the day, the features of the microcontroller is driven from the marketing end. So in the next lecture, let's explore about different types of code memories which are implemented on the microcontroller. I'll see you in the next lecture. Welcome back to the lecture. So in this lecture, let's explore about the code memory of the microcontroller. The purpose of the code or program memory is to store instructions and constant data of your program. So there are different types of code memories which are implemented inside the microcontroller. So very simplest and cost efficient program memory is ROM, that is read-only memory. There are different types of read-only memories like MPROM, which stands for Mask Programmable Read-Only Memory, EPROM, that stands for Erasable Programmable ROM. This is truly read-only memory. That means once you program MPROM, you cannot erase it. So once you program it, then it is final. But EPROM is actually erasable, but the erasing procedure is very cumbersome. You actually have to take the chip outside of your circuit, and then you have to put that under the ultraviolet machine, and then you have to pass the ultraviolet rays, and then you can erase the memory, and then you can program it once again. So that's very tedious and a very cumbersome method. So usage of EEPROM is almost obsolete. So you no longer see those kind of memories inside the microcontroller. And after that, there is one more type of read-only memory that is called EEPROM, which stands for Electrically Erasable Programmable ROM. And we just saw that it is quite famous and it is being used in some of the modern microcontrollers as well. We just saw in the previous slide that TI's microcontroller actually has on-chip 2 kilobytes of EEPROM. Even though it is called as ROM, it doesn't mean that you are not able to erase it. You can erase it. So, and the erasing technique is also very simple. So it is erased by using electric voltage. So that's why it is called as electrically erasable programmable ROM. All right, so apart from that, there is another type of code memory that is called as OTP, which stands for one-time programmable. And also these days, flash memories are very much popular in the microcontroller domain. So flash is also electrically erasable programmable ROM, but the fabrication technology which is used for flash and EEPROM is completely different. Even though the purpose is same, that is both are non-volatile and erasable writable memories, there is a difference between cost and speed. So the flash memory is being dominated as core memory in today's microcontrollers. And apart from that, there is one more non-volatile memory, that is FRAM. FRAM stands for a ferroelectric random access memory. So most of the STM32 microcontrollers, they don't have this memory as core memory. The reason is, so if you use this as a core memory, then the cost of the microcontroller will shoot up. This is costlier than flash. But the important thing about ferroelectric random access memory is its speed. The access speed is very much high compared to the flash memory. So you find FRAMs as code memory in some of the Texas Instruments MSP microcontrollers. For example, here is a block diagram of the MSP 430 FR2422 microcontroller. And here you can see that in this microcontroller, you don't see a flash as code memory. So they have used FRAM here. And it is of around 8 kilobytes. So take a look into its size. It's just 8 kilobytes. I mean, this microcontroller may be targeted for some low power, ultra low power applications, maybe. All right, so these are some of the different types of code memories which are implemented inside the microcontroller. So I'll see you in the next lecture. All right, so here we have a program. The project name is 003 add. And it's a very simple program. And here we have three global variables, and two global variables are initialized to some data. And after that, I'm just adding those two global variables, and I'm storing the result into another global variable. Here, if you look at this program, now here we have data, right? So these are the data. And after that, on the data, we are doing an arithmetic operation. And after that, we are storing the result back into the variable, right? Let's compile and let's download this code into the microcontroller. And after that, let's analyze so where exactly the data are stored and where exactly the program instructions are stored. I'm just compiling this code. So I'm just compiling the code. Let's first compile the code. And here you can see that we actually got the executable, that is .elf, right? So this is the file which we are going to download into our target. And please note that this data is also part of this .elf executable, right? So this data is actually hidden inside this .elf, right? First, let's load this .elf into the target. All right, so now let me just click on debug as STM32 MCU application. The code is actually downloaded into the target, and the Eclipse actually went into the debug perspective. So here you can see the log. So the ST-Link GDB server communicating with the ST-Link circuitry of the board, and after that, here you can see that it actually erased the internal memory, that is embedded flash, and after that downloaded the code. So basically you should see something like this: download and verified successfully. So that means the executable part of the .elf file is actually downloaded into the non-volatile memory of the microcontroller, which is nothing but flash. So now let's examine the flash contents to see whether the instructions are really stored there or not, because that is our program memory, right? So we'll first examine the program memory of the microcontroller by using our debugger. To examine the program memory, you have to take a look into the memory window. So to get the memory window, so go to Window here, go to Show View, and here you can see Memory and Memory Browser. So now let's open the memory browser. So here you have to type the base address of the program memory of your microcontroller. So what is the base address of the program memory of our microcontroller? These details you have to get from the reference manual of the microcontroller. Let's open the reference manual of our microcontroller to see the address. Alright, so open the reference manual of your microcontroller. So here the microcontroller I'm using STM32F407, and go to the embedded flash memory section. Let's go there, and you have to browse through this section. And here it is. So I get the flash module organization table. If you are using STM32 based microcontrollers, then you should see similar table, but addresses may be different or maybe same. The number of sections may be different. But if you are using some other microcontrollers from entirely different vendor like Texas Instruments or NXP or something like that, then you should be able to get the base address of your program memory. Here you can see that the embedded non-volatile memory organization. So this is actually flash memory. So this is a flash memory of 512 kilobytes. And apart from that, that is a read-only memory. So that's what we call a system memory. So user cannot write into this read-only memory. So the ST has already placed a bootloader code into this memory. So in this table, this is our program code area, and the base address is this one, and the final address is this one. From here to here, we can save our program instructions. So when you download the code will start accumulating right from this address onwards. So now let's examine this memory address, and let's see whether the codes are really present from this location onwards or not. Now I'm going to copy this address, and I'm going to the IDE, and I'm going to paste in the memory browser. After that, let's hit enter, and here you can see that this memory window is actually displaying the contents of memories from this memory location onwards. And this memory location happens to be the memory location of the flash memory, right, in our microcontroller. So this is where the program instructions or machine codes are stored. So all these are machine codes. So here you can see that all these are actually opcodes or machine codes of the program instructions. So if you want to check this memory contents byte by byte, then you can do that. So here it is showing you word by word. So that means 32 bits by 32 bits. For example, this is the contents of the location, this one, that is 0 cross 8000000. So this is the content of the location 0 cross 08000004. So like that. So if you want to check byte by byte, so then you have to do some settings here. So right click on this window and you get columns. So set the columns to 1. Now you can see word by word. If you want to see byte by byte, then again select, go to cell size and click on 1 byte. So here it is. So at the memory location, this one, the content is 0. At the memory location 01, the content is 0. So like that. All right, so that's about the program memory, right? Let's examine the data memory. The data memory is SRAM, right? So before checking the SRAM contents, we have to first find out the base address of the SRAM memory, that is the data memory in our microcontroller. So now for that, again, we have to refer to the reference manual. In the reference manual, should mention the base address of the SRAM. That is actually there in the section memory and bus architecture. I would go to memory organization. So, or you have to search by the word SRAM. I'm not sure here. So now let me search by the word SRAM. So here you can see that there are two SRAMs in this microcontroller. That means there are two data memories. Now the primary data memory is SRAM1. So that's the main data memory. So its size is 112 kilobytes for this microcontroller, and the base address is, let me search, and you have to refer to the section 2.3.1. So I think it is there in this section 2.3.1 embedded SRAM. So here you can see that SRAM1 and SRAM2 mapped at address this one. So that means in the memory map, so about the memory map, we are going to discuss later. So don't worry about that. So in the memory map of the microcontroller, this address belongs to SRAM1. That means from this location onwards, SRAM starts. That is SRAM1 starts for this microcontroller. So many microcontrollers have only one SRAM. That's okay. So all these are marketing techniques of the microcontroller. Since it is a high-end microcontroller, it has multiple SRAMs, which are used for different purposes. But the primary data memory is SRAM1, and its address starts from this memory location. Let's copy this, and let's go to our memory browser. And here, let's paste this address and hit enter. And here it is. So this is the data memory, and the data, that is minus 4000, is actually stored here. I can show that to you by changing the radix to hex, decimal signed. So let's change the format, decimal signed. And here you can see that at this location, minus 4000 is stored. And after that, at this location, 004, this 200 is stored. All right, so we actually downloaded the executable into program memory of the microcontroller, right? That is the flash memory. So the data of our program must be in flash memory, right? So how come data arrived in data memory, that is SRAM? So that's a very important question, right? So, and this actually bothers most of the beginners. So how come the data arrived in SRAM? So we have to investigate this. So as I said before, when we created the .elf file, so these data are also part of that executable file, right? And after that, we download that into the program memory that happens to be flash memory, right? So that means data is indeed stored in the flash memory. So we can see that. So now let's check where exactly these data are stored in the flash memory. Now to see that, we need its address, right? For that, let's analyze the .elf file using some of the GNU tools. Alright, so the GNU tool which we are going to use is object dump. So now run this command on your PC command prompt and you will see some information, and let's analyze that. Alright, so while executing this command, if you see this error, command not recognized, then don't worry, you can follow this method. So go to your STM32Cube installation folder. Okay, that is in the C drive, ST Cube IDE. Okay, and here go inside plugins, and here just search for GNU, and you see something like this, GNU. Okay, external tools GNU. Its name is something like this, GNU tools for STM32. Okay, so here go inside tools and bin. Okay, so here you see all these cross compilation tools, and you just copy this path, and then in your search box just search for environment variables. Okay, right. So this one, edit the system environment variables. And here go to advanced, and here environment variables, path, edit, new, and paste that link up to bin. Okay, 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 okay. And now let's try. So you see now also it gives that error, so you have to close this and reopen. Okay, and now let's try arm none EABI object dump .exe. So now you see the command is recognized. So what I'm going to do is now I'm going to open the mingw command prompt. Let's increase the font. So now let me go to the project folder. So here let's get into debug. And here that is a .elf, right? Let's analyze that using arm none EABI object dump .exe h003 add elf. So now it actually produces these results. If you can't run this executable, then don't worry. So you go to your project folder and there is already a file called .list. You just open that. So that also will give you the same output. So here it is. So you will see something similar. So if you can't able to run that command, just examine a .list file. First of all, so what's happening here? So when I run this command with -h, so what happened was, let's see what exactly is -h. So -h is actually display the contents of the section headers. So ELF format has a section. It has a section header, and if you provide -h, it will display the contents of the section headers. So our ELF file actually has all these sections. And there is a section called .text, where under this section all the codes are stored, the executable codes, or you can say opcodes or machine codes are stored under the .text section, and all the constant data are stored under the section raw data. So actually it needs some time to understand these sections. So but for a time being, just take a look into data section. So .elf has a section called .data. So this section contains the data of your program. At what address? So here it is, at this address. So this address is nothing but LMA, load memory address. The data is actually loaded into this address, and just see this address. So this address starts from 0x08, right? So that is nothing but it falls into the flash memory area. So our flash memory actually starts from 0x0800, right? So that means the data section is actually loaded into the flash memory at this address. And after that, take a look into this column. So this is virtual memory address. Now the word virtual is used because this is actually a Linux terminology. So don't give much importance to the virtual. There is nothing virtual here. So everything is physically implemented. So all memory addresses are physically implemented, at least for this microcontroller. So if you take a look into this virtual memory address, it says a RAM address. So that means it's a destination address. So someone has to move the data which is stored in the flash memory to the RAM memory. So someone has to do that. Someone did that, right? So who did that? So whether it is done by the hardware or software, the answer for that is it is actually done by the software. So the data which is there in this memory location in the flash is actually copied into the destination location in the RAM at this address. And that is actually done by our code, but we have not written any such code in the program, right? So our program is very simple. It is just adding two numbers. So where is that code? So now let's examine that later. But before that, let's copy this address and let's see in the memory browser whether it really has our data or not. So let's hit enter, and here it is. Indeed, these data are present in the flash memory. So from here, someone is copying into the data memory, and that copying of data section is taken care by the start of code of your project. So now the code is right here in the startup file. Alright, so in the startup file, so that is a routine or a function called reset handler. So all these routines are implemented in assembly level language. This startup file is given by the ST. So whenever the processor, so in this case ARM processor, undergoes reset, the first function or routine which gets called is reset handler, which is implemented in the startup code. So now this handler will get called automatically by the hardware. And this is the very first instruction which is there in the reset handler. So that means this is the first instruction which will get executed after resetting the processor. And here you can see that this is a place where data is copied from flash to SRAM. So here actually these are initialization of source and destination addresses. And after that, here is a place where data is copied from flash to the destination location that happens to be the SRAM locations. And after that, there is a BSS section initialization, that is zeroing of BSS section. So all those things we will explore in later part of the course. Now it is not required. After that, you can see that this reset handler calls main, so which is implemented in your main.c. So branch to main. So before that, it also calls standard library initialization function, that is libc init. So because we are using standard library or reduced C library in this project, right? So that's why before using those libraries, the initialization function must be called. So that is called before main. So if you are not using any standard libraries, then this branch to libc init is not required. So you can keep a breakpoint here to see data copying. So I would keep a breakpoint here. So what you can do is just go to the debug mode, and you can keep a breakpoint here. Just double click over here, and after that hit run. So let's try once again. So here it is. The code execution is actually halted at this place. So let me show that once again. So first what you do is, so the IDE is in the debug mode. So just remove this breakpoint first. What you do is first reset the chip. So now the execution halted at main. That's correct. Go to the startup file and keep a breakpoint here in the reset handler at this position. And now again reset the chip. So once you reset the chip, the code execution hangs here. Right. Now check the contents of R0 and R2, because those registers contain source and destination addresses. Now to check the processor registers, what you have to do is go to Window, Show View, and go to Registers. Here, this is a general register, so just open that, and now let's just select this, and here you can see that R2. So let's select R2, and here you can see that R2 is actually the source address, which is actually a flash address where data is stored, right? So from R2, a value or data is copied into R4, right? So you can see that R4 is minus 4000. So that's our data. And then it is stored to R0. So what is R0? R0 is RAM address. So like that, data copying takes place, and that code is added by the startup code. So with that note, I would like to end this video. So takeaway from all these lectures is that you should be able to identify data and code section of your program, and the code that means opcodes, machine codes, they actually will get stored in the flash memory, that is our program memory, and the data of your program is copied from flash to data memory, that is SRAM, from the startup code. So that startup code is actually part of your project, and that is added automatically by the IDE when you created the project. And in the next lecture, let's understand about the disassembly feature of the IDE to see various instructions generated for our code. And I'll see you in the next lecture. Welcome back to the lectures. Now let's understand about disassembly feature of the IDE. So what exactly is disassembling the code? If you check the dictionary meaning, disassemble means translate from machine code into higher level programming language. So in our case, disassemble means, so we have a tool called object dump. So we take that tool and we run that on the executable file what we generated, that is .elf file. And we can get back the assembly instructions generated for the program what we have written. This will be helpful when you want to carry out instruction level debugging. So that means if you want to see what are the processor instructions generated for the code we have written, and if you want to understand how exactly the control is passing from one part of the program to another part of the program, and if you want to check whether there is any room for optimization and all, you can do the instruction level debugging using a disassembly feature. So the IDE also gives you disassembly window from which you can observe the instructions generated. So the IDE also does the same. So it also runs object dump tool internally on the ELF file. Let's go to the IDE and let's see how to get the disassembly feature. Now, once you are in the debug mode, so what you have to do is you have to go to Window, Show View, and just click on disassembly. And here it is. So these are the instructions generated for our code. So all these are ARM instructions, or strictly speaking, these are thumb-2 instructions of ARM instruction set architecture. So please note that the processor what we are using here is ARM Cortex-M4, and the processor architecture is ARM v7E-M. That's the architecture name for the processor. This architecture uses this ISA, that is instruction set architecture, designed by ARM. And the instruction set architecture name is thumb2, which is a collection of 16 and 32 bits instructions. So here you are not seeing this cursor right here. So if you want to get that, what you can do is just click on go to current program counter, so which is right here. All right, so these are the ARM instructions which are generated for our main function. So if you just check our code, so what's happening here? So this is actually a case of read, modify, and write, isn't it? So if you observe the equivalent assembly code here, so these are the assembly mnemonics, and these are the opcodes. And this is a location where the opcode is placed for this instruction mnemonic. So if you just observe this, so this is nothing but the collection of load and store instructions, right? First, the data is read from the memory locations into the processor registers. So by using load instructions. So this is where the read takes place, reading from memory location to the processor registers. After that, this is the modify operation, add. So two registers are added and the result is placed in the register R3. And after that, this is write back to the memory location. Now the content of the R3 is written back to the memory location. So if you are not able to see this opcode, then what you can do is you just right click here and just select this show opcodes. And here you can see that even though we have written only this much of code, the disassembly is showing lots of code, right? Because you have called printf here, which actually includes codes from the standard library. So because our project also uses standard library, right? So you can also check this disassembly using object dump tool on your .elf file. For example, I can run the command arm none eabi obj dump. So just run this command and you can use the argument -d. So that is disassemble, display assembler contents of executable sections. If I run that command -d on my ELF, so here it is. So it disassembles all the code sections and gives you the assembly code generated. So you can see that there are lots of code, isn't it? So even though your program looks very simple, since you have used printf, so all these codes from the standard library are included. So our main code is right here. So this is our main code, and our main code starts at this location in the program memory. And this happens to be the first instruction of our main function. And you can see that most of the instructions are of 16 bits. And since it uses thumb2 instruction set, some instructions also of 32 bits. So for example, this instruction is a 32-bit instruction. So if you want to explore more about thumb2, so please go to the ARM website and explore about the thumb2 instruction set architecture, and the discussion is completely out of the scope of this course. So that's about the disassembly. So use it whenever you want to do instruction level debugging. Let's say I want to debug what exactly is happening at this line of code. So what I would do is I would just put two breakpoints. So one is right here. So just double click over that blue strip and put one more breakpoint right here. So here you can see that at the right hand side in the disassembly window, also there are two breakpoints got inserted, right? Now if I run the code, and you can see that all these instructions actually ran, isn't it? And I got the result. So the result is this much. But if you want to do instruction level debugging of this line, then you have to insert breakpoints in the disassembly window. Let me reset everything. Let's see, I want to see what exactly happens in these two instructions. So I would put a breakpoint here, and then I would run the code. And now let me check the register R2, because that was the affected register, right? R2. Let's check the register R2. Now let's go to the registers R2, and here you can see that. So the value from the data memory is read and placed into the internal register R2. So that is minus 4000. And if you want to see the address, then this is the address. Now let's change the format to hex. So from R3, that is the address. Value is read and placed into R2. And after that, what happens? R3 is loaded with another address. Let's see what is that address. So I'm going to remove this breakpoint, and I'm going to place the breakpoint here, next line, and I'm going to run. And R3 content is now changed to this value, right? To fetch the next value, right? After that, now let me put the breakpoint here. So now let me remove these breakpoints and let's run. And here you can see that now R3 contains 0 cross C8, that is nothing but 200. So now R2 has minus 4000 and R3 has 200. And after that, add is executed, right? Now let me keep a breakpoint here and let's run. You can see that add is executed and the result is placed in the register R3. The result should be written back to the data memory, right? To the variable result. So that's why for that R2 is loaded with the address. You can see that. Let me put the breakpoint here and let's run. And here you can see that R2 is loaded with the address. So this is the address of the variable result. And after that, store is executed. That means value is placed into this memory location, right? So you can see that in the memory location window. Let's go to the memory browser. So this contains 0. Let's execute. And here you can see that the result is placed here. So this is nothing but minus 3800. So that's how you can do instruction level debugging using disassembly. And with that note, I would like to end this video. So try this at your desk and see whether you are able to do all these things or not. And I'll see you in the next lecture. There is a quick update here. So if you want to do instruction level debugging using disassembly window, so there is one option called instruction stepping mode. So instead of keeping breakpoint at every line, what you can do is you can enable this instruction stepping mode. So just click on that to enable instruction stepping mode. So you can see that that is enabled. So now you can just use this step into option to execute the instruction one by one. So it just executes one instruction and stops at the other. So instead of putting and removing breakpoints, you can use this feature. So when you want to debug your C program, then you can disable this instruction stepping mode and you can use this step into or step over in your C program. So this is a very helpful option. So I just forgot to use that in the previous lecture. So you can make use of that. So I'll see you in the next lecture.